Hello and welcome to the webinar. I'm Ann Thayer, contributing editor to the CNEN Media Group, and I'll be moderating today's event. This webinar is entitled An Introduction to the Theory and Practice of LC Method Translations and LC Method Transfers, and it's being sponsored by MacMod. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you're disconnected during the webcast, please log in again according to the instructions you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I'll be posing as many as time permits. Please note that CNEN does not endorse any company products or services that may be mentioned in the webinars, and that each webinar will be archived at CNN Online after the live webcast. The presentation today is being sponsored by MacMod. MacMod's mission statement is Smarter Chromatography, which means that it partners with customers to offer innovative solutions to complex problems. The company uses advanced analytical software to match its product portfolio with the customer's separation needs. It leverages 30-plus years of experience in the LC column business and its technical expertise in manufacturing network to help solve application problems. And it provides up-to-date and accurate technical catalogs and reports from leading separation scientists to keep clients informed of new technologies. During the presentation today, we'll hear from Gemma Lowe, Senior Product Manager at HiChrome UK. There she is a key part of the business development team with responsibility for leading a range of HPLC and UHPLC training events and seminars across Europe. Gemma has over a decade of experience working in the HiChrome technical support team, troubleshooting chromatography methods, recommending suitable column chemistries, and supporting the wide range of HPLC and UHPLC columns in the firm's portfolio. Originally a biochemist, her focus areas include the analysis of biomolecules by various chromatic techniques and the analysis of polar analytes. I will now hand things over to Gemma.
Thank you very much for that introduction, and thank you for MacMod for inviting me to speak about method translations, some theory and practice. So there are many reasons why we might want to transfer our method, our HPLC method, to a UHPLC method, for example. One of those main reasons is time. And time is money in the industry. If we can do things more quickly, but with the same performance, then we can have lots of benefits in terms of productivity compared with the original method. So one reason we might want to translate our method is to get some more time to speed things up to make increase productivity. There's other things that we may want to do. We may want to transfer a method from HPLC to UHPLC, or we could just look at speeding up an HPLC method or potentially a UHPLC method as well. Perhaps we want to go the other way. So our lab, we have a lot of UHPLC systems, but we want to outsource the work. We want to use a different company for the manufacture of the product, and they don't have the same liquid chromatography capabilities. So maybe we want to transfer our method from UHPLC to HPLC. We may be interested in the solid core particle format, so superficially porous particles. And when you transfer a method from your standard porous particle to one of these solid core particles, you do need to change the method to get equivalent chromatography. So we're going to take advantage of the solid core particles, the efficiency, the speed, the low back pressure, but we need to change the method slightly to make sure that we're actually getting the same performance, the same efficiency, the same separation, same selectivity, for example. Perhaps we want to have a faster method development time. Again, speeding things up is really beneficial to us as an analyst and to our companies. So if we can develop methods faster, especially if we have a lot of methods to develop coming in, then that's going to be of benefit to us. We can reduce the overall cycle time. Perhaps we want to translate a method to get more resolution. We want to get a higher peak capacity, more peaks in our separation. So for a complicated sample, this is really beneficial if you can have narrower peaks and better resolution. So we can use these translation principles to achieve a higher resolution separation. Finally, not every instrument in our lab is from the same vendor. So we might want to run the method on different vendors' instrumentation. And it's the same method, but it might work slightly differently on each instrument. So we need to know what things to consider when we're translating our methods from one instrument to another instrument. And that can be just another HPLC. It doesn't mean it's moving from HPLC to UHPLC. It could just be another HPLC system from a different supplier. So we need to consider those certain parameters to make sure the method works accurately and reproducibly on both systems. So we're going to start with isocratic translations, and there are less things to consider in isocratic methods than there are in gradient methods. But all of the principles that we learn here really are of benefit to our gradient methods. So for an isocratic method, if we want to translate the method from a large column to perhaps a smaller column, the key parameter that we need to remain consistent is this length to particle size ratio. And what I mean by that is shown quite nicely in this table. Each column format has a certain potential efficiency. So a 30 centimeter column with 10 micron particle size has the same efficiency as a 15 centimeter 5 micron particle size column. What that means is both of those columns should give us the same performance chromatographically if we translate the method correctly. And you can see from this table at the bottom of the slide the lists of efficiency related to this length to particle size ratio for different format columns. So it tends to be that the longer the column or the smaller the particle size, the more efficiency that format has. But you can see there are very big differences in each of the column formats. So within the red boxes are those columns that have a length to particle size ratio of 30,000. So we should be able to translate our method from each of these column formats and achieve the same separation, so the same chromatography. The benefit for us of moving to the smaller dimensions is time. So we can save time and we can save solvent as well. So that's a big benefit for us financially and with time. And if you want to have a look at the reference at the bottom of this slide, then you can see this is a recognized way of translating methods as per the United States Pharmacopoeia. It's a revision that was put in a few years ago now to help us to really scale down methods. So there are things we need to consider in our actual method. The first one is to know the volume of our column. So we can experimentally derive the column volume, or we can estimate column volume. And this is going to be dependent on whether you have a fully porous particle or a superficially porous particle column as well. So that will change the volume of the column. So we need to scale our injection volume if we're changing the column volume. And we also need to scale our flow rate. Now, this is related not only to the particle size change, but also the column ID change. We can work out the new runtime for our method using this equation here, and we can also estimate the back pressure of a new method. So this will really help you see whether your instrumentation is actually capable of running that column with that particle size at that specific flow rate. Because a lot of the time when we are scaling methods, we reduce the particle size of our column, and when we do that, we increase the back pressure. So although it's great because we are reducing solvent and we are reducing runtime, we have to pay with something, and that is back pressure. So I'm going to work through an example because I think that explains this translation much more readily. But the equations that you see here are all relevant as we go forward. So this is our original method. These are some methoxybenzene isomers run on an HPLC column, 150 millimeters, 5 micron particle size, and 4.6 millimeter ID. So we have an isocratic method with a runtime of 35 minutes. And you can see the structures of the analytes at the bottom of the screen. The critical pairs are peaks 1 and 2 and peaks 4 and 5, but both have a resolution of 3 or above. So they're well resolved critical pairs. And you can see the other details in the top box. So for our column, which has this pentafluorophenol bonding, the column dimensions give us a column volume of nearly 1.6 mils. And the length to particle size ratio is then 30,000. We want to scale this method to UHPLC. So what we need to consider is the column we're going to choose. And in this case, it's the same column chemistry, but we are going to a smaller particle size, so down to a 1.7 micron particle. And the column dimensions are 50 millimeters by 3 millimeter ID. So that column format has slightly less length to particle size ratio, so 29,000 instead of the 30,000. And the column volume is much smaller, so 0.223 mils. So you can see this building up in the table at the top of the screen. As I mentioned, the column volume is best to be experimentally determined, but you can use this equation at the bottom to estimate the column volume if you don't work it out yourself. So first thing we need to do is use those column volumes to scale our injection volume. And you can see here it's related to the ratio of the column volume times by the original injection volume of 5 microliters. So it makes sense. We're going to a smaller column, so we're injecting less material onto our column. So now we want to inject only 0.7 microliters. There is the potential that you could inject more, but for a academically correct method translation, you should reduce the injection volume proportional to the column volume as demonstrated. We then want to scale our flow rate. Now here we've changed both the column ID and the particle size. So we are timesing our original flow rate by the ratio of column ID and the ratio of column particle size. So this is suggesting we need to run at a higher flow rate of 1.25 mils a minute. You can plug those numbers into this equation for runtime, and it's suggesting the final runtime will now be 4 minutes. And again, you can work out back pressure using all of the values that we've already seen. And this is suggesting now our original method of 66 bar back pressure is going to increase up to 559 bar. So this is telling you much higher back pressure. Perhaps I definitely need to run this on a higher pressure system, a UHPLC system. So what does that look like? Well, it works. You can see when we run the same scale that we've saved a lot of time. Our runtime is below 5 minutes. And if we drill down to the specific peak pairs, we are still achieving the same chromatography, just in much less time. In fact, we've saved nearly 89% runtime. So we've maintained the resolution of the critical pairs, we've maintained the efficiency of our peak 6 in this occasion that we were looking at, and we've saved a lot of time and a lot of solvent. So it really is beneficial, and this is why UHPLC is becoming so popular, because we can achieve much faster separations with the same chromatography we had in HPLC. So here it translates the injection volume and the flow rate, and you should get the equivalent chromatography in a faster runtime. But we do need to have a higher pressure system to run this type of column. Again, if you are working with UHPLC, but your contract lab perhaps only has HPLC, then you use these same principles, but you go backwards, you go the other way. And you can translate the method back to HPLC quite readily. Now, we worked very hard to generate a calculator that had all of these formulas built in the background so that you don't have to remember each of the equations. So this is the method translator tool that we've developed that you can download on the MacMod website. And you just fill in any of the highlighted boxes with your original column dimensions and particle size. Then you put in the new column dimensions and particle size. You make sure you write whether it's porous or superficially porous, and it can translate the method for you. So it basically has all those algorithms in the background to translate the method for you. And you can see this is the method we just looked at. So a 15 centimeter 4.65 micron going down to a 5 centimeter 3 millimeter ID 1.7 micron. So it tells you what your new injection volume should be and your new flow rate as well. So it's all those equations that I've shown you just in a handy tool that you can use. So in terms of what the pharmacopoeia lets us do with our methods, some of these USP methods were written some time ago and have very long run times. So we'd quite like to speed those up. In 2014, there was a big update to the monograph that allows you to actually use these translation principles for isocratic methods. And what they've said is that we can change the column if we maintain this length to particle size ratio, or if we are within minus 25% and plus 50% of the length to particle size ratio. So that example that I showed you didn't have exactly the same value as the length to particle size ratio, but it was still within the specifications for an allowable adjustment to the method. There's also a further update, which means that you can change even further outside of these specifications based on the efficiency of the original peak of interest. That means that for isocratic methods, we can use a lot of different columns. Gradient methods, there's not that flexibility. So if your monograph states a gradient, then you have very little flexibility on the method column that you can use without having to do a revalidation. One other thing just to note is that not all columns work very well on all instruments. What I mean by that is if you are using smaller ID columns, it's really critical that the dispersion of the instrument is very low. This is why the UHPLC systems are very good, especially if you go to 3 mil or 2.1 millimeter ID, because they have less extra column volume within the system. And we'll touch on that again later. So here's an example of quite an old monograph, which states C18 column, 300 by 3.9, 10 micron particle size. And you can see the method takes 8-9 minutes, and it's an isocratic run. We wanted to speed this up, so move to a 15 centimeter, 4.6 millimeter, so more standard ID, 5 micron particle. So the equations here we've seen before. We're scaling the flow rate and the injection volume based on the different columns that we've chosen. So it's suggesting a higher flow rate and a smaller injection volume. And what you can see when we put that into practice is you get a resolution value above 2, which is the monograph specification. You get percentage RSDs within the required range, and you've saved quite a lot of time, so perhaps half the run time. And this is not going as extreme as UHPLC, it's just going from quite a large, big particle size column to a shorter, smaller particle size HPLC column. Within the monograph, now we can go to more extremes of the length to particle size ratio. So we don't have to stick to that 30,000 in this case. Actually, within this box, there are many more columns, column formats that we could choose that still meet the USP guidance. So let's have a look at what that does chromatographically. Well, here we have a column that's got a lower length to particle size ratio. So here it's only a 5 centimeter column with 2 micron particle size. But it is still separating out our 3 analytes of interest and meeting the requirements from the monograph. So we have a method that's under 1.5 minutes, and it does everything that we need it to do. So you see you've saved a considerable amount of time. The back pressure is over double what we had originally, but it's still within the usable HPLC limits. If we look at something with a higher length to particle size ratio, you see here we have 40,000. So we've gone for a longer column, 100 millimeter length with 2.5 micron particle size. And this ultra core format, this is the superficially porous kind of fused core format. And here you can see again, my run time is below 2 minutes, but I've got taller peaks, I've got more efficient peaks. And that's what this length to particle size ratio is really telling us. We've got a higher efficiency here. So both of those methods could be considered and still stay within the required USP specifications, so our resolution and our percentage RSTs. Again, just consider any negative effects of band broadening if you are going to the small column format. So here's another isocratic translation that we'll go through quite quickly. We're looking at a fully porous C18 column, the Super C18 in this instance, on a standard HPLC system. And we've got a 20-minute runtime. What we want to do in this case, and what we're allowed to do according to the pharmacopoeia, is actually move from a fully porous phase to a superficially porous, so a solid core phase. But we're going to move to a column of exactly the same format. So it's still the same dimensions, still the same particle size. It's just the actual particles within the column are now solid core instead of fully porous. So in terms of the method translation, we don't need to change the flow rate because we still have a 5 micron 150 by 4.6 column, but we do actually need to scale the injection volume because our solid core column has slightly lower column volume than our fully porous column. So here's the results from that experiment. We have run the same sample on both columns. All we've done is adjust the injection volume. So we've got a lower injection volume for the solid core, and we've turned up the sampling rate on the detector because we've actually got narrower peaks, so it just describes those a bit better. And you can see here, we've actually got okay resolution for the earlier eluting peaks. Not quite as good as our original method, but the final peaks have come in a lot sooner. They've eluted a lot more quickly, and that's really made them much more efficient. So we've got much higher plate numbers, so N numbers for the later eluters. And the runtime has been halved compared to our original method. Now, this difference is really related to the hydrophobicity of the column. Because you've got a lower surface area, you've got less carbon load on that superficially solid core type column. That means that you've got a reduced hydrophobicity of that phase. So we've actually speeded up the runtime and improved our efficiency of the later eluting peaks by moving to the solid core format. So we could speed this up using the translation principles that we've already learned. In this case, we went for a 75mm column, so halved the column length. We halved the particle size, so now went to a 2.5 micron instead of the 5. And we reduced the column ID from a 4.6 mil to a 3.0. Now, this actually lost the resolution for the early eluting peaks. And if you look, we've specified which instrument we used here. This was because our system actually didn't cope very well with moving to a smaller ID column. So there was too much extra column volume going at the lower flow rate on the smaller ID. So if we stick with the 4.6 mil ID column, as demonstrated here, we actually get better resolution, especially for those early eluting peaks. And we, again, halved the runtime from our 15 centimeter solid core phase. So this is what I was talking about earlier with the negative effects of smaller ID columns. So just if the results aren't what you're expecting, perhaps go back to a 4.6 mil ID, because that is pretty forgiving on instruments that even have higher extra column volumes. Okay, so the second part of this talk is on gradient. And everything that we've been through is still relevant for a gradient method. So we still need to know the column volume, we still need to scale the injection volume, and we need to scale the flow rate. In addition, for a gradient method, we need to maintain a constant K star. What I mean by that is we don't want to change the selectivity when we're running our method. So we have to use this TG equation, point 4 on this slide, which takes into consideration the column volume, the flow rate, and the gradient time, TG. So we need to think about that equation as well. We also need to consider the dwell volume in the instrument. And this is important for standard methods on the same system, if you're changing the column dimensions, but it's also important when you move from one instrument to another. So here we have an example. We're moving from a porous C18 amide column in this case to a smaller column, and we want to translate the gradient method. This is a 45-minute gradient time, and the critical peak pair, peaks 9 and 10, have a resolution of 2.9. We've specified the average peak capacity here, as that's a good measure of our kind of how many peaks we can get into a separation window. The more peaks you can get in that window, obviously the sharper they will be, the narrower they are, the more efficient. So we know our column volume, and we're going to move to a shorter column from the 250 to the 150 millimeter length, and we're going to move from a 5 micron to a 3 micron particle size. We've experimentally derived the column volumes as shown here, and we're using that to translate our injection volume, just like we did for isocratic methods. So we've got a smaller injection volume, and we're also going to change the flow rate based on the ratio of column ID and particle size, exactly the same as we did for isocratic. So here it's suggesting a increased flow rate of 1.67 mils a minute. The difference we have with our gradients is this gradient time. And you've got all of the values you need from the first experiments, the first equations, to then plug those numbers into this gradient time equation. So here, our 45-minute gradient time is multiplied by the ratios of column volume and flow rate, and it's suggesting that our new gradient time is 15.87 minutes. Now what that looks like is the original method, but faster. So again, gradient translation shouldn't be taxing, they shouldn't be hard work if you follow these principles. Scaling the injection volume, scaling the flow rate, and making sure that the gradient time is correct based on those values. So here you can see we have a good peak capacity, and we have good resolution of our peaks 9 and 10. We saved a lot of time, and we saved a lot of solvent. Here you can just see some column volumes, and this is based on the columns in our range, but obviously you can experimentally derive whichever column you're using. Something you need to consider is the fact that these solid core phases tend to have about 13% less volume. So it's a smaller column volume in these columns. So moving from a porous column to one of these solid core columns, again, everything is the same. These equations are the same each time. The other point we've put on here is considering the dwell volume, column volume ratio. So we'll look at that as we go forward. So our original method, fully porous, 20-minute gradient time on a 15 centimeter column. We've moved to the solid core, same dimension, same particle size, but we've adjusted the gradient time and the injection volume because we've got a different porosity. So we've got a different column volume here. And you can see you can speed up the method just by moving to a solid core phase. You can then use the translation principles, go even faster by changing the column dimensions. And again, you've maintained the resolution and the peak capacity is okay, but you've done this now in 7 minutes compared to the original 25-minute method. You can double the flow rate, and that halves the gradient time. Now I've got a 3.5-minute method. Obviously, you need the post time after the gradient, but you really can speed up some of these older methods or start your new methods really on a much smaller column format. So something to think about is when you choose your new column dimensions, potentially that new column has a much smaller volume than your original column. And if you run that on the same system that's got the same dwell volume, this equation at the top is misbalanced. So we ideally want the same dwell volume over column volume from our original method to our new method. If we don't have this, then we need to use the new column volume and the flow rate to either delay the injection or add an isocratic hold at the start of the method. And what this does is make the analytes see the same profile. They see the same isocratic gradient that they would on the original method. If you've got a big mismatch here, then your analytes are seeing a different profile, and that results chromatographically in a change in selectivity often, poor resolution, peaks moving around, because you haven't maintained the same, K star is not the same profile that the analytes are seeing. So that's better described in an example, I think. Here we have a 5 micron C18 column, C18 PFP, 15 by 4.6, 15-minute gradient time, and 1 milliminute. We've moved this onto a much smaller column, so only a 5 centimeter column now with a smaller particle size, and had to modify the method to include a delayed injection. And that was determined by the equation at the bottom of the screen. So this tells you that the column has actually been run on a different instrument. You can see that by the different dwell volumes stated as VD1 and VD2. But the ratio of the first system dwell volume over the column volume less the new system dwell volume and the new column volume is a mismatch. So we have to times that by the new column volume over the flow rate, which suggests that we need to start the gradient and then inject after the gradient started, because the dwell volume, or the difference between the systems is significant. If we don't do that, what happens is we lose the resolution. We don't achieve the same separation if we haven't modified this gradient because of the different volumes. So this is where we can see errors when people are moving their methods to shorter columns, especially when the dwell volume on the different systems is significant. Fantastically, within the gradient translator tool, it does all this for you. So you need to measure the dwell volume on your original system and your second system. Obviously, that could be the same if you're using the same instrument, but you type in the numbers here and the calculator will actually tell you whether there's a significant difference that means you need to modify the start of the gradient. And that fits nicely with our instrument transfers, really. We're moving an isocratic method, we shouldn't need to change the method, obviously, unless we do any translation. When we move a gradient method, if the dwell volume is different, on one system and the next, then we might need to modify the start of the gradient. So here's just an isocratic method run on 2 of our UHPLC systems. You can see the resolution, the efficiency is approximately the same, even though the 2 systems have slightly different extra column volumes. If they've got significantly different extra column volume, potentially you might see broader peaks on the system that's got more volume, more dead volume. When I talk about dwell volume, I mean the point at which the solvents mix through the autosampler to the head of the column. So on a binary system where you've got high pressure mixing, you can see the area, the box in yellow, is the dwell volume of your instrument. So this dwell volume can be small, it can be large. This is a binary system on a quartz system where you have low pressure mixing. It could potentially be bigger because you have the pump and the autosampler in that fluid path. These can be slightly different on instruments. We tell our system to do 5 to 95 in 3 minutes. What it does is flushes through the dwell volume and then does 5 to 95 in 3 minutes. So you can see here the same instrument with different setups have a different system dwell volume. So the analytes see a different gradient profile because they see a different isocratic at the start. And you can see here just some typical values, but I would suggest you measure the dwell volume for your specific instrument. It can vary depending on whether you change the mixture, whether you change the tubing, things like that as well. So what we need to consider is if the dwell volume between one system is different to another. So this is our original method, VD1 minus VD2, so dwell volume of the second instrument, divided by the flow rate. And you can see if that X value is negative, we need to delay the injection. And if it's positive, we need to add an isocratic hold. If I show you this, this is my favorite slide. It actually describes it a lot more clearly. What you want the analytes to see is the same isocratic, so ideally the same dwell volume at the start, followed by the gradient profile. Now, if your second instrument has a bigger dwell volume, ideally you want to delay your injection. So if it's negative, delay our injection to artificially shorten the dwell time. If our second system has a smaller dwell volume, then we want to introduce an isocratic hold at the beginning, so inject earlier, and then we have added dwell. And what that means is your analytes see the same gradient profile. Just to show you that with a nice example to finish, here's some vanillin running a very fast gradient, so 1.6 minute runtime here, 1.32 minute gradient. And you can see the critical pair has a resolution just below 2, so 1.7. We're moving that from our quartz system to a binary system. The binary system has a lower dwell volume here, you can see from the equation. That gives us a positive value, so we need to add an isocratic hold at the start of the method. The flow rate tells us how long that should be. Here's what happens if you don't correct for the flow rate, for the different dwell volume. We just run exactly the same gradient profile on both instruments. And you can see the resolution is lost. So now it's only a resolution of 1. If we add in that isocratic hold at the start, so you can see actually in this gradient table, we've added 0.29 minutes of isocratic. Now my selectivity is restored. I've got the same method I had on my original instrument, and I'm happy because I can now run this on 2 systems in parallel. The calculator does this for you, so again, you don't have to do it yourself. You just make sure that you've got accurate dwell volumes when you are filling out the gradient method transfer box. This is the same example. It's just showing you that we can run it on lots of other instruments. So changes selectivity if you don't do a pre-gradient hold. And again, it doesn't mean it's the same vendor, it's different vendors' instruments. We have to translate the method because of the different dwell volumes. We might need an isocratic hold, we might need to pre-inject. And some systems allow you to do that, others don't. So I have come to the end really. Hopefully I've shown you isocratic translations are quite straightforward. Gradient translations are a little bit more involved, but they shouldn't be scary. And also I've shown you how we can do method transfers between instruments as well. There's lots of knowledge notes, there's lots of resources that you can download that really walk you through all of this. So please do visit the resources section on the MacMod website to download not only the translator tool, but all of the information about it. I would like to thank you all for your attention, and I'm going to run a couple of polls, I think, at the end of this before we take any questions in the last few minutes. So again, just do have a look on the website and do contact us if you have any specific information requests. So I've just got 2 polls just to run, if you wouldn't mind filling these out on your screen. The first one is, would you be interested in learning more about ACE UHPLC columns? Yes or no? A lot of the examples that I've shown today are on the ACE column platform, but obviously other vendors are available. And the last question that I want to ask is, do you feel like you learned something new about UHPLC method development today? And with that, if you could just spend a few minutes filling that in, I will pass you back to our moderator and see if there are any questions from today. Thank you very much.
Thank you, Gemma, for a very interesting presentation. And as you mentioned, we'll now move to Q&A and do as many as we can. First question is, does the dwell volume also need to be considered in the SEC GPC method?
That's a very good question. In terms of translating an SEC method from one instrument to another instrument, a lot of the methods I've seen are gradient methods, so I would definitely consider that. Sometimes they've been moved from an SPLC type system to an HPLC, and those would have dramatically different dwell volumes. So I don't think we've done any work on it here, but yes, I would definitely consider measuring the dwell volume and compensating for it on an SEC method.
Someone asks, other than examples between UPLC and HPLC, do you have any examples for analytical HPLC to prep LC?
That's a very good question. Actually, I have been doing some work on preparative HPLC, and I did test out the translation calculator to see if it worked, and it does work. The big difference, I would say, with analytical and prep is that we're normally overloading our column when we're going to prep. So the recommended injection volume from the calculator is probably lower than what we actually will inject in reality, because we're trying to get more product from the column. So it does work, and the methods translate well. I've got some examples which I could forward on afterwards. But yeah, it doesn't have a function for overload within the calculator.
Someone asks, when considering changes in the VDVM in gradient translations, will you always correct by delaying the injection?
If your instrumentation allows you to do that, then we will. If it's suggesting maybe 1 second, 2 seconds, then it's not worth our time. If the value is negative, we need to have the delay. If it's positive, we need to have an additional isocratic step. So it could be the other way around, depending on whether, I guess if you were going to a prep column, for example, you might have a bigger column volume the next time compared to an isocratic, compared to an analytical.
Someone asked whether, regarding the transfer of gradient methods, do the translation equations apply to the separation of peptides?
Yes, it does. We have done some work with peptides. They do behave in most cases like small molecules, and the translation does work. The only thing I would consider was if they're quite large peptides that have any secondary structure, because then you might see some differences. So it will depend on how big the peptides are, but it should, in theory, translate well, yeah. We've also done it actually for coupling columns together. So we've translated methods from 1 column to 3 columns in series for protein digest, so peptide mapping.
Someone asks whether you need to consider dwell volume for the isocratic method.
No, not really at all. The only slight difference may be the peak shape if you have a lot of extra volume in the system, but for isocratic methods, it's not really a concern. We do measure the dwell volume on all of our systems during the annual maintenance, so even if they're for isocratic runs, but I wouldn't anticipate that we needed that value really, no.
Another person asks, between the method translation, is the RRT changed?
Sorry, can you repeat that question, please?
The question was, between the method translations, is the RRT changed?
So the retention time, I might need to come back to that one. I'm not really sure I understand the question. The retention time will change when you're translating methods if you change the column volume. So if you're actually changing the column dimensions. And even if you keep the same dimensions and move through systems, you might change the retention time if that was the question.
Okay. One that's a little more straightforward maybe. What would be the best way to measure the dwell volume in the systems?
We actually have a nice ACE application knowledge note on how to do that. And there is a tab within the translation tool that walks you through the method. You basically run a gradient with acetone, and it shows you, then you work out the midpoint, and it gives you a value for your dwell volume. So I'd again encourage you to have a look on the resources section for that knowledge note.
Someone asks, when converting your gradient time, how do you account for hold times within the gradient? Do you treat the gradient on either side of the hold time as its own gradient time?
So if it's a multi-step gradient, maybe I'd consider it that way. So you need to translate each step of the gradient, and that can be whether it's a slope or an isocratic part. So there is a factor that you can use to then make sure you're translating each step of the gradient, which will include those isocratic parts. Again, this fantastic tool. It does that for you, so you can put in the isocratic holds, you can put in each of the steps of the gradient, and it uses this like conversion factor to tell you what the new gradient should be and how long each of those isocratic holds should be, especially if you're changing the runtime because you've changed the column ID, for example.
Okay. The person who asked the question about the method translation and the RRT being changed sent in a note and said they were referring to the relative retention time.
Oh, relative retention. Okay, sorry, I apologize, I missed that.
That's okay.
In terms of the relative, in terms of the relative retention, I think if you're translating it just to go to a smaller column dimension, the relative retention time should remain consistent, and that's really where I think the USP has been coming from. If we keep the same length to particle size ratio, then all of our peaks should be moving in the same way. We are achieving the same separation, just in a faster time. If you start changing other things in the method, then obviously your relative retentions can move around. But yeah, they should, in theory, be the same because you're getting the same separation.
Someone asks if you'd be able to explain again how to correct for porosity for translating gradient methods.
Okay, no problem. It really depends on which brand you're working with as to how porous the column is, and it relates to the column volume. So the porosity is only going to change the volume of the column. What I mean by that is when we work out column volume, it's basically the volume of a cylinder, so pi r squared h, times by this porosity factor. Now, some vendors will specify the porosity factor. You'll see in the slides I've used a porosity of 0.55 for the ACE version of this solid core, and then 0.63 for the fully porous. But the only way you're going to work that out for, unless the vendor tells you, is you'll have to experimentally derive the column volume. And you can work backwards from that if you want to then work out the porosity value for that specific brand of column. Hopefully that makes more sense.
I know you showed some translations between different systems, and someone asks, I don't know if this one was covered, someone asks whether you have data on a conversion between a 1290 to an acuity.
We have both instruments in our lab actually, so we definitely would have data. It will depend on the setup and the specific modules that they're using. But it is possible to do method transfer between any instrument. You just need to make sure those 12 volumes are measured. You also, some systems are better at solvent mixing, for example. So there are some other things to consider, as well as the dwell volume when you're moving between systems. But maybe if they are interested in some specific data, we can talk offline on that model.
I think we'll do just one last question, and that is, how do you handle step gradient translations? Does the calculator do that as well?
Yes, yes, I did mention some aspects of that. It will translate based on a correction factor, so a conversion factor for each of the steps within the gradient. So yes, the answer to that question is you can use the translator, no problem, for any number of steps. And also, if there's not enough boxes there, we can always add more boxes to the steps. It's an easy thing to add.
Well, that's terrific, Gemma. Thanks so much for handling all those questions. And thank you, participants, for being a great audience. Be sure to check CNN or CNN Online for information on the next edition of CNN webinars. Our thanks to On24 for technology and production services, and to MacMod for the sponsorship that made this interactive webcast possible. For CNN Webinars, I'm Ann Thayer. Have a good day.